Hi everyone, in this recording we'll be going over operations matrices. Our goal is that by the end of this presentation you'll be able to determine whether two matrices are equal, add and subtract matrices and multiply matrices by scalars, multiply two matrices, use matrices to transform vectors, and use matrix operations to model and solve real-life problems. A matrix can be denoted by an uppercase letter such as A, B, or C. They can also be denoted by representative elements enclosed in brackets. So for example, we have A subscript ij enclosed in brackets. And lastly, a matrix can be denoted by a rectangular array of numbers such as the one provided. So two matrices, A equal to Aij and B equal to Bij, are equal when they have the same dimension, so m by n. And every entry, Aij is equal to Bij for I between 1 and m and j between 1 and n. So now we're told to solve for the entries A11, A12, A21, and A22 given the matrix equation. So the two matrices are equal when their corresponding entries are equal. So A11 is equal to 2, A12 is equal to -1, A21 is equal to -3, and A22 is equal to 0. So in order to be sure that two matrices are equal, they must have the same dimension and their corresponding entries must be equal. So for example, we're given two 2x2 matrices. And on the left-hand side, the entries are 2, -1, square root of 4, and 1/2. So on the right-hand side, the corresponding entries are 2, so 2 is equal to 2, -1, -1 is equal to -1, 2, so the square root of 4 is equal to 2, and 1/2 is equal to 0.5 in decimal point form. But here we're given the matrix with entries 2, -1, 0, 3, 4, 0 on the left-hand side, and on the right-hand side, we're given the matrix with entries 2, -1, 3, and 4. So we see that on the left-hand side, this matrix has 3 columns, where on the right-hand side, the matrix has 2 columns. So the matrices cannot be equal. For matrix addition, if we are given the matrices A and B, both with dimensions m by n, then their sum will also be an m by n matrix, and we will be adding the corresponding entries. So A plus B will be equal to Aij plus Bij. The sum of two matrices with different dimensions is undefined. So now we're given some examples. So example A, we're given two 2x2 matrices, so their sum will also be a 2x2 matrix. So the first matrix has the entries -1, 2, 0, and 1, and the second matrix has the entries 1, 3, -1, and 2. So adding the corresponding entries, we'll have -1 plus 1, which will give us 0, 2 plus 3, which will give us 5, 0 plus -1 will give us -1, and 1 plus 2 will give us 3. For the second example, we're given two matrices, both having 2 rows and 3 columns. So both of them have dimensions 2 by 3, so then the resulting sum will be a matrix of 2 by 3. So for the first matrix, we have entries 0, 1, -2, 1, 2, 3. And for the second matrix, they are all 0 entries. So that means the sum will just be the first matrix. Now for the third example, we are given a matrix with 3 rows and 1 column, so 3 by 1. And we are adding by its additive inverse. So 1 plus -1 will give us 0, -3 plus 3 will give us 0, and -2 plus 2 will give us 0. If we are given the matrix A with size m by n and C a scalar, then the scalar multiple of A by C is the m by n matrix C times A. So we will just be multiplying C times every entry in A. So here are some examples that we can work with. So for the first one, we are multiplying 3 times every entry in A. So 3 times 2 will give us 6 for the first 2 entries in the first row. 3 times 4 will give us 12. 3 times -3 will give us -9. 3 times 0 is 0. And 3 times -1 is -3. Now 3 times 2, 6. 3 times 1 is 3. And 3 times 2 is 6. Now for example B, we are told to multiply by -1. Or that is the same thing as just flipping the signs of B. So now -B will be 2 times -1, so -2. Zeros will stay the same. 1 times -1 is -1. -4 times -1 is +4. 3 times -1 is -3. -1 times -1 is +1. And 3 times -1 is -3. And 2 times -1 is -2. Now for example C, we are told to multiply 3 times A and subtract B from that product. So since we already have both components, we can just add them. 3a plus negative b, or 3a minus b. So starting with the first row, 6 minus 2 will give us positive 4, and 6 minus 0 is 6, and 12 minus 0 is 12. Now with the second row, negative 9 plus negative 1 is equal to negative 10. And I was adding them because same signs, add and keep. So now 0 plus 4 is equal to 4, and negative 3 plus negative 3, negative 6. 6 plus 1 is 7, 3 plus negative 3 is 0, and 6 minus 2 is 4. So I rewrote all the matrices so it's easier to follow. So first I have 3a minus b. So I kept the b positive and the minus on the outside, so you can just distribute the negative sign. And this is the resulting matrix. So here are the steps and the solutions to the examples that we just worked through. Here are the properties of matrix addition and scalar multiplication. So we let A, B, and C be matrices of dimension m by n, and let C and D be scalars. So the first property is the commutative property of matrix addition, meaning the order of the addition does not matter. So A plus B is equal to B plus A. The second property is the associative property of matrix addition, meaning the grouping in which we add the matrices will not affect the answer. So A plus B plus C, where B and C are in parentheses, is equal to A plus B, where A and B are in parentheses, plus C. The third property is the associative property of scalar multiplication. So that means the grouping of the scalars will not affect the answers. So C times D times the matrix A is equal to C times D times A. Now the fourth property is the scalar identity property, meaning 1 times A is equal to A. Now the fifth property is the distributive property. So if we have a scalar and we're multiplying by the sum of A and B, then we can distribute the C into both matrices and add C times A plus C times B. The sixth property is the distributive property once again, but now we are summing the two scalars, so C plus D, and multiplying them by A. So we can do C times A plus D times A. Now, one important property of addition of real numbers is the number 0 is the additive identity. So that means C plus 0 is equal to C for any real number C. So for matrices, a similar property holds. So if we have the matrix A with dimension m by n, and 0, the m by n 0 matrix consisting of entirely zeros, then A plus 0 is equal to A. Here we'll be going over an example of solving a matrix equation. So we are told to solve for x in the equation 3x plus A is equal to B, where A and B are the following matrices. So A is a 2 by 2 matrix with entries 1, negative 2, 0, and 3, and B is a 2 by 2 matrix with entries negative 3, 4, 2, and 1. So first we begin by solving the matrix equation for x, meaning we will isolate the x. So first we move the A to the right hand side, so we subtract by A on both sides. So now we have 3x is equal to B minus A. Now we can further isolate the x by dividing by 3 on both sides, so x is equal to 1/3 times B minus A. So now we can substitute the matrices A and B. So for B, we plug in the entries negative 3, 4, 2, and 1. And for A, we plug in the entries 1, negative 2, 0, and 3. Then we complete the subtraction. So negative 3 minus 1 will give us negative 4. 4 minus negative 2 is positive 6. 2 minus 0 is 2. And 1 minus 3 is negative 2. So now we can do the scalar multiplication. So when we multiply 1/3 by every entry in the resulting matrix that we just got. So 1/3 times negative 4 is negative 4 over 3. 1/3 times 6 is 2. 1/3 times 2 is 2 over 3. And 1/3 times negative 2 is negative 2 over 3. So if you're given a matrix A with entries Aij that has dimensions m by n, so m rows and n columns, and the matrix B with entries Bij with dimensions n by p, so n rows and p columns, then the product AB will be an m by p matrix. So it will have the number of rows from A and the number of columns from B. Now here's the definition for how to compute each of the entries for A times B, but that may look confusing without practice, so we'll go over an example to define the process. So an important thing to note is that the number of columns from matrix A, so the number of columns from matrix A, should be equal to the number of rows from matrix B. So for our example here, we have a 3 by 2 matrix for A, and for B, we have a 2 by 2 matrix, and we see that the columns from A match the rows from B, so that means we can multiply, and our matrix AB will be a 3 by 2 matrix because we are using the rows from A and the columns from B. So now for the process. So to find an entry, we will use one row from the first matrix, so we'll use this row from matrix A, and one column from the second matrix, so the first column from matrix B. Then we will multiply matching numbers, so we will do -1 times -3, and 3 times -4, and then we will add them. So -1 times -3 is +3, plus 3 times -4 is -12. So that'll be the first entry in the first row. So we just found C11, and that was equal to A11, so this one right here, times B11 right here, plus A12 times B21. And that's just this portion right here that we did. So that simplified 3 minus 12 is equal to -9. And now we repeat the process for the entries right here, since we'll have a 3 by 2 matrix. So we found the first entry in the first row by doing -1 times -3 and adding to 3 times -4. So now to find the entry right here, the second entry in the first row, we will still use this row, and now we will multiply by the second column. So we'll do -1 times +2 and add that to +3 right here times +1. So 3 times 1. And now that'll be the second entry in the first row. So -2 plus 3 is +1. So now for the second row, we do this row by this column. So we'll do -3 times +4, which is -12, plus -2 times -4, which is +8. So -12 plus 8 will give us -4. Now we do this row by this column. So we'll do 4 times 2, which is 8, plus -2 right here times 1, so that'll just be -2. So that'll give us +6 for that entry. So now for the last row, we do this row by this column. So 5 times -3 is -15, and we don't have to write 0 times -4 because that'll just be 0. So now we do 5 and 0, and 2 and 1. So 5 times 2 is 10, and we don't have to do 0 times 1. So that'll be -15 and 10. And that is our matrix AB, so 3 by 2. So here are the steps that we followed for the example that we just did. But when you're looking at this, make sure to not confuse that with multiplication. These are each separate entries. So this one corresponding to there, and so on. So we see we got the same answer, and a matrix of size 3 by 2. The n by n matrix that consists of 1s on its main diagonal and 0s everywhere else is called the identity matrix of dimension n by n, and it is denoted by the capital I with subscript n, and we see that it has 1s all along its diagonal and 0s everywhere else. So note that an identity matrix must be square. So when the dimension is understood to be n by n, you can denote in simply by I. So if A is a square matrix, meaning it has dimensions n by n, And the identity matrix has the property that A times the identity, having the same size, will be equal to A, and the identity times A will also be equal to A. So we have the example here. We have a matrix A of size 3 by 3. So when we multiply it by the identity, I3, we get A once again. On the right hand side, once we multiply first the identity by A, then we also get A. So now we can use matrices to transform vectors. So that can be done by rewriting a vector in its column matrix form. So we're given the vectors V with entries 2, 4, and W with entries 6, 2. So for example A, in order to find V plus W, we can first convert each of the matrices, the vectors into column matrices. So V will equal to 4, so it'll have 2 rows and 1 column, and W will equal 6, 2 with 2 rows and 1 column. So now we can simply add each of the entries just like we did with matrix addition. So 2 plus 6 is 8 and 4 plus 2 is 6. So we will have the column matrix 8, 6. Now we can flip it back to get our vector. So now it'll be 8, 6. The same concept applies for example B, but now we will multiply 2 times V. So it'll be scalar multiplication times the column matrix for V. So 2 times 2 is 4, and 2 times 4 is 8. So now we can subtract that from W. So 6 minus 4 is equal to 2, and 2 minus 8 is equal to negative 6. So we have the column matrix 2, negative 6, and now in vector form it'll be 2, negative 6. Matrix multiplication can be used to represent a system of linear equations. So we're given this system right here on the left-hand side, and that can be represented by the matrix equation AX is equal to B, where A is the coefficient matrix and X and B are column matrices. So X is the matrix we're solving for, and B are the constants. So what they mean by that is that we have on right here, the A is the coefficient matrix, so each of the coefficients times X. So when we do matrix multiplication, we choose the first row of the first matrix times the first column of the second matrix. So we did A1 times X1 right here, and sum A1, 2 times X2 plus A1, 3 times X3 right here. And we're setting that equal to be 1. And we repeat that for however many rows however many rows we have. And in our case, we had 3 rows. So we can use these equations and methods that we learned to solve for the matrix X. So now going back to the augmented matrix, pretend this is it rewritten in augmented form. So we had the constant on the right-hand side and the coefficients on the left-hand side. So in our example, that happens when we adjoin the matrix B right here to the matrix A. So that's what we get on right here. A on the left-hand side and B on the right-hand side. So now the matrix X, where X is adjoined to the identity matrix and X is each of the solutions, that represents the reduced row echelon form of the augmented matrix that yields the solution to the system. So in our previous example, we had our augmented matrix, then we performed elementary row operations, and we got our identity on the left-hand side and the solutions on the right-hand side. And I don't remember the exact constants, but we had the identity on the left and the X on the right. So that means, in our case we had X, Y, Z, I believe, but here we're working with X1, X2, X3. So that means we have X1 is equal to 1, X2 is equal to 2, and X3 is equal to 3. So this is what they mean in this portion right here, and how that yields the solution of the system. So now here's an example. We are told first to write the system as a matrix equation. So we stated that A is the coefficient matrix, and X is the matrix that we're solving for, and B is the matrix with the constants. So we see here for the first equation, we have constants 1, -2, and 1, which is why we have this row for our coefficients. And we have the variables x1, x2, x3, so that's why we have x1, x2, x3. And we see that the first constant, b1, is -4. So now, repeating that process, for the second equation, we do not have an x1 right here, so we'll just have a 0 for the first entry in the second row, we have a 1 for x2 right here. So that's why we have a 1 there. And a 2 for x3 right there. And then our constant is 4. So now for the last equation, we'll have the row 2, 3, negative 2 in our coefficient matrix and 2 in our constant matrix. So that is the matrix form AX is equal to B. So now we had join the matrix B to matrix A, so the constants to the coefficients, and then using Gauss-Jordan elimination, we obtain the reduced row echelon form. So we have the identity matrix on the left-hand side and the X column matrix on the right-hand side. So that means our solution is x1 is equal to negative 1, x2 is equal to 2, and x3 is equal to 1.